recording started. Go.
Okay, why computer science and engineering majors make great neuroscientists? What are you going to know by the end of this? What a neuron is, how the electrical signals go across it, how can we model it, what does the math look like behind it, and then how do we code up all that math? So if we look at a neuron, okay, it takes in electrical signals. Those electrical signals then go across an axon, which have various ion channels across them. That electrical signal then goes out to the dendrites, and they come in through a synapse to the dendrites. This is an all or nothing. It fires or it isn't, and it builds up. Essentially, these electrical impulses build up, our brains and our thoughts. So, how does that work? We have a bunch of ions on both sides of that membrane. So across, there's an inside and an outside of that axon. The ions travel in. We start off with a resting where we have sodium on the outside, potassium on the inside. The sodium rushes in when the neuron starts to fire. Then we keep going. The potassium rushes out, and so we went from sodium rushing in to increasing the potential across it to now potassium rushing out, lowering the voltage across it. And then we have the sodium potassium pump that gets us back to the original state. And so if you look at that as a translational thing, the sodium rushes in, which shoots the voltage up, and then the potassium rushes out, which lowers it back down, and then it goes back to its resting state. So that's the depolarization and repolarization of the cell. Now, to model this, we take a giant squid back in 1952 by Hodgkin and Huxley, which they were able to create this circuit. Now, this is a relatively simple circuit. We have a capacitor, and then we have a couple of the ion channels, and we model it with circuits. So, electrical engineering, this is exactly what it is. We took the biology and created it into a circuit. How do we break that apart? Well, now we take the math of that circuit and we can model it. We have a channel, for the potassium and the sodium, and we can model that as currents. We have a leak current that's kind of like the extra part of the circuit that keeps it at that resting potential. And then we have that capacitance, and this sums up for the current across the membrane. We can take all this. We note that, our channels are only open so much, and that's what the gating variables are, the N, M, and H, which then have their own set of equations. It's really complicated. It's not important that you memorize them. It's more important that you understand it's a complicated set of differential equations that models it. From there, we can also look that there's a lot of other models to go through this. The MRG model is excellent, and the integrate and fire model is another one. But we can take all these models, notice that they're all based on differential equations, and because of that, we can use implicit integration to approximate the equations. We can use things like forward Euler, backward Euler, or the Crank-Nicolson method to approximate the equations using a variable time step. And with all of that math, we can throw it into one of these programs, and that's how we would model it. And so programming a circuit is neuroscience, at least computationally. So computer science and engineering majors are great at neuroscience.
End of TLDR.